Hello, this is Professor Dan Kernler again. This is our second video in section 17.6. We're going to do some surface integrals, and I have my goal for this video to do 2 problems. Hopefully we can keep it under half an hour. So if that tells you anything about these, well, just let that sit out there. So we're going to do two surface integrals, two specific examples, and let's jump right into those now. So first one, we're going to find the surface area of a torus. It's kind of a cool problem. We're going to have a circle radius A. So the A is a constant here. It's in the YZ plane, and we're going to revolve it around the Z axis, where the circle's centered is on the Y axis at a distance of B from the Z axis. So again, B is a constant as well. So you have A and B. If you go up to the definition here of a surface integral, you can see if our function that we're integrating over the surface is 1, we get the area. So we're going to let our function be 1. But our first big challenge is we need to parameterize this surface. We need to define our torus, our entire donut. We need to define it in terms of 2 parameters. Okay, well, let's pick a point x, y, z on our surface. We would like to get x and y and z defined in terms of 2 specific values, 2 specific variables. So first of all here, let's take a look. If we have u is this angle, we're given a little hint here, then the z value will be, let's see, we could do, what would we do there? We would do sine of u would be z over a, so z is equal to a sine u. So we have one coordinate taken care of. Let's see here. If you'll notice here, we have b is this distance, and then we have the other side of that triangle. That's the x coordinate. So let's see here. Well, not quite. Need to hold that thought. But let's see here. Let's take a look here. So that will be, that's not quite the y coordinate either. So, but hold that thought. I want to get that total distance out. That's, if I go over to the drawing on the right, that's this distance right here. This distance right here. So let's think about that. Let's see here. Yeah, that's this distance right there. Let's see here. Let's find the bottom portion here. We said that, let's see, the z value there, sine of u was z over a. So that means if we do cosine of u, should be that, whatever that question mark is, over a. So that question mark should be a cosine u. So that means this distance out here from the origin out to directly, in the xy plane, underneath our point, should be b plus a cosine u. So then our final challenge is to figure out, okay, that's like underneath the point. So now I need to get what the x and y are. So I think I'm going to try to squeeze this over to the side here. If we look in the xy plane, x, y, if you're looking at this from above, right? So you have your distance out here. This is the b plus a cosine u. And then you have v is the angle from the positive x-axis. And we can do the same kind of analysis here. You have the x coordinate is going to be that times cosine of v, and then the y coordinate will be that times the sine of v. So parameterizing, it looks like we can take b plus a cosine u times cosine v, that's the x. The y will be b plus a cosine u times sine of v. And then the z we said was just a sine u. Incidentally, this is not a trivial example for a student to do on their own. Just an example for us to do together. The ones that you will have will be a little bit more manageable than this one. But what we have here, this is a parameterization of the torus. Now we do need some restrictions for u and v. So u is the angle from the positive y-axis, actually like the xy plane basically, up and around. So u goes from 0 to 2 pi. And then v is the angle looking from above from the positive x-axis, and that has to go all the way around as well. And so again, you'll recognize, or you'll notice here, that in the UV plane, this is a square. So the domain of this is actually a square. The domain of this surface is a square. To find the surface area, our f of x, y, and z will just be 1. Okay, so looking up above here in the integral, we need the tangent vector in the u direction, we need the tangent vector in the v direction, and we need their cross product. And then we need to find its magnitude. Yes, that is why we have a lot of workspace here. Okay, so let's be conservative with workspace. The tangent vector in the u direction, that's the partial derivative of x with respect to u, partial derivative of y with respect to u, partial derivative of z with respect to u. All right, let me scroll up just a little bit. That was not just a little bit. All right, that will be, let's see here, in the u direction. Okay, so looks like that'll be b minus a sine u cosine v. Know what? Nope, change my mind. B is constant, so the derivative of the b will be 0. So we'll just get negative a sine u cosine v. And then the derivative of y with respect to u, very similar, negative a sine u sine v. And the derivative of z with respect to u will be a cosine u. Okay, seems rather innocuous. All right, tangent vector in the v direction. This is the partial derivative of x with respect to v, partial derivative of y with respect to v, partial derivative of z with respect to v. Okay, partial derivative of x with respect to v. Let's see. Well, we're going to have a negative sign because of the cosine v, b plus a cosine u, and then sine v. And then b plus a cosine u cosine v. And then the derivative of z, that's nice, that's 0. The rest of it looks, I need to like bleep out something, doesn't look good, but at least the z coordinate is 0. Now, I have some bad news for you. Now, we need to find the cross product, yes, the cross product of those two vectors. We have I, j, k, and then we have negative a sine u cosine v. I thought I left plenty of space. Negative a sine u sine v. I did not leave enough space. Sheesh. Okay, a cosine u. All right, and then negative b plus a cosine u sine v, b plus a cosine u cosine v, and 0. Oh, boy. Okay, so for the I, we will kind of, usually when I'm doing these myself, hold my finger over the first column. Then it would be negative a sine u sine v times 0, that's good, minus, and then let me put a bracket there, b plus a cosine u cosine v times a cosine u. All right, and then minus j, and then again we'll cover the j up, and then we'll go across, let's see, 0, nice, minus, I guess that becomes plus b plus a cosine u sine v times a cosine u. Okay, plus k times, and then we cover the last column up. Oh, no 0 this time. Negative a sine u. Oh, we're going to get a cosine squared v, right, because of that cosine v. And then b plus a cosine u minus, dear Lord. Oh, it is still minus because there's two negatives. Then b plus a cosine u. There's another sine u sine squared v. What? Well, I know what the answer is. Do we need, I don't know if we have time to do all this. Oh my gosh. I don't think, and then we have to find the magnitude of that. This is a bad idea. I have the magnitude written down. I don't know that I want to go all the way through the video finding that magnitude by hand. I don't think you want me to either. So we are skipping A, simplifying all of this mess, and then B, finding the magnitude. That would be another like 10 minutes probably. Okay, so I'm just gonna give that to you. It's A times B plus A cosine U. Now that seems super simple, like how is that possible? But you have all these trig functions squared in there, so you start factoring out stuff, you get ones, some like terms cancel out. You find the magnitude, so you're squaring each one, so you got more squares, so it's plausible at least. Okay, now we're ready to do our surface integral. We have the double integral over the region. Our function is 1. We have the cross product, the magnitude of the cross product, b plus a cosine u, and then we have dA. So that'll be double integral. Both of them were 0 to 2 pi. I guess we can pull the a out in front. B plus a cosine u du dv. All right, that's my a out in front, 0 to 2 pi. We're integrating u first. Bu plus a sine u from 0 to 2 pi, and there's still a dv hanging on that. We'll have b times 2 pi, so 2 pi b minus b times 0, so that's gone. And then a times sine of 2 pi, which is 0, minus sine of 0, which is 0. Oh, so we just have 2 pi b dv. So that will be 2 pi ab times v from 0 to 2 pi. So 4 pi ab is the surface area. Oh, there's an extra pi squared. Sorry, 4 pi squared. 4 pi squared AB. 4 pi squared AB is the surface area of a torus, where the, like, kind of like if you slice the donut, that cross-sectional radius is A, and then the radius from the inside of the donut out to the middle of the donut, the hole to the middle, is B. Wild. Okay. All right, let's do one more. This video is already 13 minutes. Okay, the next one. Suppose the temperature on a sphere of radius A varies according to the function T of phi theta is 10 plus 50 sine phi. You can think of this on a sphere. So what this would be is, remember, phi, that's like the worst sphere ever. Here. Okay, that's marginally better. I don't know. It's been a long day. Okay, so phi, remember, is the angle from the positive z-axis. So when phi is 0, it's the coldest, and then it gets the warmest at the equator. That would be 60, and then it increases down to when sine of pi is also 0, and then it's 10. So it's like 10 at the poles, 60 in the middle. So kind of plausible, of course, very much simplifying what the temperature of the globe is. So this is not necessarily the Earth here, but that's the idea. Okay, so we're going to find the average temperature over the poles. The difference between just doing the surface integral here to find the average temperature is we need to find 1 over the area and then times the double integral over the region of the temperature. That, okay? Oh, no, temperature weighted by the surface integral is what I meant to say here. Let's not use phi and theta. Let's use the temperature function multiplied by the magnitude of the cross product of the tangent vectors dA. All right, surface area of a sphere, we're actually not going to do that as a triple integral. The surface area of a sphere is 4 pi r squared. 4 pi r squared. Ours is radius a, so ours will be 4 pi a squared. So we're going to put that in for the area when we're done. We do need to get a surface, and we have already done this in example 3. Get that written down here. A sine u cosine v, a sine u sine v and a cosine u with u from 0, u is v, so u from 0 to pi, and v from 0 to 2 pi. So let's go try this process. I think we're going to try to do this one all the way through. We'll do our best to see if we can simplify this one. I think we'll be able to do this one all the way through. It's a little bit simpler. The torus is actually harder. All right, tangent in the u direction. That'll be a cosine u cosine v, a cosine u sine v, and then negative a sine u. Tangent in the v direction, negative a sine u sine v, a sine u cosine v, and then 0. Zeros are great. All right, now the cross product. Tu cross product with tv. I, see if I can spread them out a little bit more, j, k. A cosine u cosine v, a cosine u sine v, and then a cosine u. And then negative a sine u, kind of see my work there, sine u sine v, and then a sine u cosine v, and then 0. Okay, let's see here. We'll have I times, let's see, 0 minus a squared. See, oh, I'm missing. Oh, I put the original one there. I'm like, wait a minute, something's not right here. So a sine u, that's why you do this work ahead of time. All right, I apologize, I had the wrong coordinate there. Wrong coordinate for tu, the z component there. Definitely should be negative a sine u. Okay, now we're ready to do the I component of our vector. The 0, j will be gone, and then it'll end up being plus a squared sine squared u cosine v. All right, minus j times another 0, and this one will still be minus a squared sine squared u sine v, plus k, and then nothing great here, a squared sine u cosine squared v. Maybe fit it in below, and then minus actually becomes plus a squared sine u cosine squared, or sorry, sine squared v. All right, sine squared v. All right, and then simplifying, let's see here. I guess we get, let's write it maybe here, a squared sine squared u cosine v, and then that becomes plus, so a squared sine squared u sine v. And then you'll notice for the k, there's an a squared sine u cosine u, and if you factor that out, you'll have cosine squared v plus sine squared v, which is of course 1, so we just have a squared sine u cosine v. It's not, could be worse, I guess. All right, so now we need to find the magnitude of that. So the magnitude of that cross product, that'll be the square root, and then we have to square each of these. So a to the 4th sine to the 4th u cosine squared v plus a to the 4th sine to the 4th u sine squared v plus a to the 4th sine squared u cosine squared v. Okay, this is great. There is a lot of good stuff happening here. If we look at the first two, they both have an a to the 4th sine u. We could factor that out. We would be left with cosine squared v plus sine squared v, which we know is 1. And then we have a to the 4th sine squared u cosine squared v. Oh, this is even good. This is good too, because you can factor out an a to the 4th sine squared u. And then you're left with sine squared u plus, oh, no. Nope. That is not quite right. I think I messed something up here. Because I'm like, this is supposed to be good. Okay, what did I mess up? Oh, there it is. There it is. Did you catch it earlier? So when we were looking at the k component, we have a squared sine u cosine u. We factor it out. Cosine squared v plus sine squared v will be 1. We have a squared sine u cosine u. Kind of do that in red there so you can see that should be u. And so this is u. Okay. Moment of panic. Okay, and so now this should be a u. Do that one in red too. You can see that correction. U. And so we factor out a to the fourth sine squared u. We're left with, there's still a sine squared u here. There's a cosine squared u, so that's 1. And then after all that, we get a squared sine u. You may want to put absolute value there. That's not crazy. That's a good idea. But sine u, when u is from 0 to pi, is never negative. So we do not need the absolute value. Okay, now we are ready to do our surface integral. Okay, so that will equal the integral. Let's see. We have the temperature function is 10 plus 50 would be sine u, right? Because phi is u. And then we have the magnitude, a squared sine u, du dv. U goes from 0 to pi, that's phi. And then v goes from 0 to 2 pi, that's theta. I think what I will do is factor out the a squared and then distribute the sign. 10 sine u plus 50. I guess I could have factored a 10 out, couldn't I? Why don't we do that? 10. We just have sine u plus 5 sine squared u du dv. I think we're going to need a power reducing identity here. 10a squared integral from 0 to 2 pi, integral from 0 to pi. What will that be? Let's see, we'll have sine u plus 5, I guess it becomes 5 halves times 1 minus cosine 2u. That's a power reducing identity. Power reducing sine squared theta equals 1 minus cosine 2 theta over 2. So that's what we did there. Okay. 10a squared, integral from 0 to 2 pi, and then we integrate, we'll get negative cosine u plus 5 halves. 5 halves integral of 1 will be u. And then we'll have 5 halves times, I guess, 1 half sine 2u, right? The derivative of sine 2u is cosine 2u times 2. So we need the 1 half there to counteract that. Okay, and this is all from 0 to pi and then dv. Okay, negative cosine of pi. Cosine of pi is a negative 1, so that's 1 plus 5 halves pi minus 5/4 times 0. That's good. Minus negative cosine of 0 is negative 1 plus 0 minus 0 dv. Looks like we get 10a squared integral from 0 to 2 pi. We'll get 2 because we have the minus and negative 1. So we have 2 plus 5 halves pi dv. And that's actually just a constant. We'll get 10a squared 2 plus 5 halves pi times v from 0 to 2 pi. Which means 10 a squared 2 plus 5 halves pi times 2 pi. And I guess we could distribute the two. I don't know, I have this written 10 pi a squared times 4 plus 5 pi. Okay, not done, almost done. That is the surface integral of the temperature. We just found the surface integral of the temperature, kind of like total temperature. We want to divide by the surface area to get the average temperature. The average temperature will be 1 over the surface area, which we said was 4 pi a squared. We have that up above, times 10 pi a squared 4 plus times 4 plus 5 pi. And I have that here, a decimal approximation that is about 49.3 degrees. I believe we are Celsius here. Ooh, it's not given to us. That would actually, no, that can't be Celsius. That'd be really, really hot. It's got to be Fahrenheit. It's got to be Fahrenheit. Man, I don't know. If I was listening and watching this, I probably would need to rewatch parts of that to totally get all of that. There's a ton of algebra, like trigonometry. This uses a lot. It definitely uses a lot. So that's my tip there, is probably to go back and rewatch parts of that so you can follow. Make sure you don't lose the big picture of what we're doing. We were finding the average temperature, which we said was basically the total temperature, the surface integral of the temperature, divided by the surface area. So to get that surface integral, we needed to parameterize the surface, find tangent vectors in the direction of both parameters, find the cross product of those, find the magnitude of that cross product, then integrate our function times that cross product, and that got us this total at the end of 10 pi a squared 4 plus 5 pi. Divide that by the surface area to get the average temperature. All right, that's it for this video. There will be one more video in this section with some additional applications and examples of surface integrals.